knock out 10.1.2. This is actually 2 days. It's part 1 and 2. We'll kind of describe as we go. It's kind of I don't know, interesting thing to do here. So, investigating data representations. The field of statistics is the application of probability theory to make sense of large quantities of data. The study of statistics allows us to make decisions and predictions from the natural variability in data. A statistic is a numerical fact or calculation that is formed from a large quantity of data. A mean or a correlation coefficient is a statistic. We're going to talk about those as we kind of go through. In this section, you will continue your study of statistics by modeling a golf tournament. So this is something that we would have done in a group as a class. We went outside with a bunch of pennies, 40 holes of golf. The Hook and Slice Corporation is having its annual charity fundraising event. In order to encourage donors to attend, the Hook and Slice organizes a fun game called 40 Holes of Golf and gives away prizes. Each team plays 40 holes of golf. There is a prize for a team. The team that is consistently closest to the hole. Your teacher has set up a hole. Your team will swing 40 pennies towards the hole, and you will then represent your data on a graph with numerical statistics. Analyzing the statistics will help you decide which team was the most consistently close to the hole. So essentially, we would have had two groups, throw 40 pennies each. We would have tracked their data, and then we would have compared their data to each other. Obviously, we're not going to go outside and all throw pennies, so I'm going to give you some of that data. And I'm going to give one set of data, not two. We'll manipulate the one, and then I'll make up like a second one and talk about if we were comparing it, what it would have looked like. I just don't see the benefit of going through the same thing twice. So your task, your teacher will give you 10 pennies. Again, not doing that. What I'm going to do is give you data that would show what it would have looked like. You would have stood 200 centimeters from the hole. The team member will toss all 10 pennies one at a time towards the hole. No do-overs and no practice shots are allowed. Record the distance from the center of each penny to the hole to the nearest centimeter, even if the penny rolled far away. So the idea being here that we're going to get some outliers, right? Some of them are just going to sort of toss and end up right next to the hole. Others are going to end up on their end and roll away, and we're going to get, some big distribution of data from how far it is from the hole. Have different team members repeat this process until 40 pennies have been tossed. Do not take turns tossing pennies. Each team member should take all 10 turns. Record your data in a safe space. You will need it in the next lesson. Decide how you want to represent your data on your poster. So essentially what happens is we end up getting this data, and I'll see if I can open this without freezing the program here. So we're going to get this data. So you can see some are going to be really close to the hole, and some end up rolling really far away from the hole. And we need to figure out what's a good way to represent this data. And so the book gives us some suggestions that we should consider. We should consider a dot plot. And actually, that's not a bad one. We're not going to end up choosing a dot plot, but it's not bad. You basically say, here's how far away it was from the hole, and here's how many times that happened. But obviously, we have a lot of variation on that, so the dot plot would look a little bit crazy, but still not a bad idea. What about a box plot? It turns out we're actually going to use a box and whisker plot. So we'll talk more about this later, but this will give us an idea of what the middle is, what the quartiles are, what the minimum and the maximum is. I don't know how familiar you guys are with those terms. You're supposed to be pretty familiar with them, but if you're not, we'll discuss them briefly. Again, obviously, it's all over the internet for you to discuss kind of what these things mean and come up with that. We have a pie chart. Pie chart isn't going to help us a lot. That's if you want to break a hole down. We have a scatter plot, which we did in chapter 4, and that's 2 variable data. We only have 1 variable data. We're just basically saying how far away from the hole it landed. So we don't have an X and a Y. We only have an X. So this isn't going to be super helpful. Histogram we're actually going to choose. We're going to put these things in groups and say, hey, it missed by 20 centimeters. It goes in that group. It missed by 50 centimeters. It goes in that group. So histogram and a box plot are the 2 that we're going to choose. We also could choose a bar graph. Although bar graphs are very similar to histogram, there's some subtle differences, one being that they connect and a bar graph has space between. I think these are more for groups as well. So that's what we're going to do with this data. We are going to take this data and we're going to make a histogram. And then above the histogram, we're going to do a box and whisker plot. So at this point, 10.1.2 part 1 is over. We've gone out, got this data. We come back the next day, which begins now, for 10.1.2 part 2, where we're going to take this, make a histogram with a box and whisker plot on top of it, and sort of go from there. So when you make a histogram, we're going to make the histogram first. There's really not a rule per se. Like, how many columns should I have? Should the columns be 10 wide and I have a bunch of them? Or should the columns be 50 wide and I only have a few of them? That wasn't 50 wide. So again, should they be 10 wide where I have a bunch of columns? You can see that's going to leave me with a bunch of columns. Or does it make sense to have them go, and by the way, it's called bin width. Does it make sense to have a bin width of 50 so I have a lot less columns? Or maybe even I want a bin width that's even farther. Maybe I want a bin width that goes by hundreds. So I hardly have any. Right? So that's one of the decisions we need to make. And usually what's considered is you take the square root of all the numbers of data. It doesn't matter that they add up to this. I'm just saying there's 40 pieces of data. And the square root of 40 ends up being about 6.3. So that would mean we would have 6 to 7 groups. But actually, we're going to end up with 8. I think, again, and there's no set rule on this. You might have done something slightly different, and that would have been fine. It doesn't mean that you're wrong. I don't know why that won't erase. There it goes. Okay, so what I decided to do was go by 20s. So 1, 2, 3, 4, 5, 6, 7. And then what I decided to do was to go 8. And 8 is going to be anything more than 140. I don't need to make the column width that wide, even though it goes from like 154 to 269. I just need to make it a little bit wider so you know that this represents 20 pieces of data each, and this one represents even more. So again, I decided 1, 2, 3, 4, 5, 6, 7, 8. If you wanted to go by 25s, that would have been fine. Again, I think 10 would have been too many. Maybe going by 30s wouldn't have been a bad idea. Again, there's more than one correct answer here, so you want to come in close to the square root of the numbers of the data. Again, I got 6 point something and I chose 8, and that's fine. So now what I want to do is I'm going to use the scale. By the way, I'm going to ignore these zeros here. So over here is my number of, and over here is going to be my distance from the whole in centimeters. So my first one, I'm going from 0 to 20. I have 1, 2, 3. So I will go up to 3. My next one is 21 to 40, or 20 to 40. And we'll talk about what it means if you end up in the middle. So 1, 2, 3, 4, 5. So this one is going to look like this. Now I go 40 to 60. I have 1, 2, 3, 4, 5, 6. And now I get this question, what do I do with these 40? Do I put the 40s in here? Wait, I screwed something up here. I'm sorry. My phone is buzzing. I'm getting a bunch of text, and it is distracting me, and I apologize, which, if anything else tells you should be putting your phones away in class. So when I go to 20, I have 1, 2, 3. That was correct. Maybe I wasn't wrong. Geez, maybe I'm just totally distracted now. So when I go 20 to 40, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And this is where I was getting screwed up. 12, 13, 14. Do I put these 40s in this side or on this side? And that's a decision that you're going to have to make for yourself. And I'm going to explain to you why I chose to put them in this column. And what matters is that you're consistent. So my logic is this. Mine is going to go from 0 to 20. Technically speaking, I could have had a 0 here, right? I could have got a hole in one where it landed in the hole. So I'm going to go from 0 to 19 and 20 to 39 because that will be 20 pieces. That'll be 20. I'll go 40 to 59. That'll be 20, right? If I instead go 0 to 20 and then 21 to 40 and 41 to 60. The problem with that is this is 21 pieces of data, and now I'm going to 20 pieces of data. So I don't want my first column to be a little bit wider and have one more piece of data than my second column. So I don't think that's a great idea. I'm going to go with this over here. So you can see I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 here. I hope that makes sense. Maybe kind of look at that and do the math if it didn't. Oh boy. Oh boy. You know what I wonder if I shouldn't do is go to the straight line tool. It might not be a bad idea to make this look better. All right. So next, I'm here. Again, I've given the explanation for why I'm doing it the way that I'm doing it. And I have to stay consistent on that now that I've chosen it. So now I'm going to go 40 to 59. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I get 11 again. I'm going to go 60 to 79. So 1, 2, 3, 4, 5. And again, you'll notice I'm choosing to make this 80 go in this bin so I can stay consistent. So 1, 2. And then now 100 to 120, I have none, so I'll leave that one blank. And then 120 to 140, I have 2 again. So it will look something like that. And now, like I said, I'm going to make this last one a little bit wider. So I have 1, 2, 3, 4, 5, 6. So again, I'll go up to 6. And then I'll go a little bit wider. And I should probably mention at this point that these numbers no longer have value and that this is 140 plus. So anything more than 140, and again, I can see that's going to tell me this thing is going to stretch. And again, you could have gone out and done it that way. If you could have gone by 20 all the way up to 269 if you wanted. There's a bunch of different ways you could have done it, but that's what we're going to do. So this is the histogram. Now what we're going to do is we're going to put a box and whisker plot on top of it. And I don't know how well you remember a box and whisker plot, but essentially you're going to have the smallest number, which obviously in this case is a 2, right? You're going to have the largest number, which obviously in this case is 269. We're going to have the median, which again is the middle. That does not mean the average. That's the mean. We don't want the... So essentially what we're saying is, oh, all right, we're working our way into the middle. And I'll tell you right now, I'm about to go by columns. So those 5 cancel out those 5. These 5 cancel out these 5. These 5 cancel out these 5. And now I'm kind of working my way back. And you can see what I'm left with is these 2 for the middle. And hopefully you guys remember, when you have 2 for the middle, what you do is you add them together and divide by 2. So if I add 47 plus 49, I'm going to get 96. I divide 96 by 2, and I get a median of 48. And then from there, what I need to do is I need to mark where my median happened. So my median happened like right here, right? As I went from here to here. So quartile 1 and quartile 3 are essentially medians for the smaller half and the bigger half of the data. So again, these 5 are going to cancel out these 5, and I'll start working my way till the middle. And what's the halfway point between 33 and 34? It's, of course, 33.5. So that's my quartile 1. And then I'm going to do the same thing over here. These cancel out, and these cancel out. Working my way into the middle. So I want the halfway point between 78 and 80. Again, I wanted the halfway point between 33 and 34, and that's going to be 79. So I hope it makes sense on how to get the median. And again, once you have that cut in half, you get the median of this, you get the median of this. It presents some interesting questions that we usually talk about in class, like what happens if you have, actually I don't want to do that. What happens if you have a... I just said I don't want to do that. 5, 8, 9, 10, 11. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. What happens if I have an odd amount of numbers? Well, those are going to cancel out. Those are going to cancel out. Those are going to cancel out. Those are going to... So my median would just be 7. Well, what happens if I have an even amount of numbers? So that cancels out, that cancels out, that cancels out, that cancels out. I take the average, right? So the same thing holds true when I'm doing quartile 1 and quartile 3. So in this example, these cancel, these cancel, these cancel, these cancel. So my median goes right in between. No numbers cancel here. So when I do quartile 1, I just ignore all this data over here and I just go cancel, 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 quartile 1, cancel, 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 quartile 3. However, and I know I'm going through a lot right now, so maybe slowly kind of watch this video again and see if this makes sense. What happens if I have an odd amount of data? Well, these are going to cancel. These are going to cancel. I'm sorry. Let me kind of clean this up a little bit. And I know I'm extending the video here and I apologize for that. Just want to make sure that we're all on the same page here. So these would cancel, these would cancel, these would cancel, these would cancel, these would cancel. This would be my median. Well, now that 8 is gone. So when I go to quartile 1, that's going to be quartile 1, and that's going to be quartile 3. So you can see sometimes the median goes between numbers, and those two numbers don't get deleted. Sometimes it is a number, and that number does get deleted. So kind of interesting how that works. Again, hopefully you guys know that, and that was just a waste of time. But if you don't, that is how you do it. So jumping back over here, I am going to go with my straight line tool again. Again, I'm just going to go above it a little bit. So the smallest number was 2. And again, that was really close to 0. So if you think about it, like each of these little lines is what, 5, 10, 15, 20. So 2 is going to be really close to the line here. That number's 2. I'm going to put another one at 33.5 again. 25, 30. So 33.5 is a little bit closer to this one than it is to the other. 48, well, there's 50 right there, so 48 is going to be just shy of that. 79 is going to be very close to 80. And 269, well, obviously 269 is way over here somewhere. So when I do my box and whisker plot, it's going to look something like the following. And again, we can now sort of look at this data. I know that this is, I know that this is 2, this is 33.5, this is 48, this is 79, and this is 269. So when I compare this data, I can say, oh look, half of the numbers were less than 48. A quarter of the numbers were less than 33.5. 3/4 of the number were less than 79 centimeters from the hole. But the last 25% of the numbers, boy, they had a big spread on those last 25%. So let's say this is data A. And let's say we wanted to compare this to data B. And let's say data B had the following, right? We would have gone through all this stuff again, figured out quartile 1, quartile 2, median quartile 3. But I didn't, like I said, I didn't want to go to that much trouble on this. So what if we got the following data? So I could make another box and whisker plot, right? For data B. Again, this is data A over here. So let's make another one for B. I have one at 6. It'll be a little bit further over. I have one at 10. I have one at 22. I have one at 50. And I have one at 80. Now this would be pretty dramatic. I wouldn't expect something like this to happen in class. where it would be so one-sided. But this number is 6, this number is 10, this number is 22, this number is 50, and this number is 80. And what we'd say is, okay, well, which one won? And I think for most people, we could easily say, well, B won, right? The worst miss is way closer than the worst miss here. The middle, the first 3 quarters are way better here, right? You got 75% of the data were only 50%. So 3/4 of your throw were just as good as their best half of their throws. My best half the throws on B were better than 1/4 of the throws on A. Obviously, quartile 1 is way smaller than quartile 3. The only case, but this is what's interesting about this, and this is why I made it the way I did, you could make an argument for A, because the best toss overall was an A. So maybe you could say, well, yeah, A's team is terrible, but the best thrower is an A. You could make that argument, but other than that, I think you would definitely have to argue that B is better. So I hope this makes sense as far as how you take this data, you make the histogram, you make the box and whisker plot above it. Again, this is like a side view, whereas a box and whisker plot is like a top view, sort of like looking down. So this is a side view of a roller coaster. This is the top view looking down on that same roller coaster, right? It goes up. This is where a lot of the data is, then it goes back down. You can see it goes up. So, and then it goes back down. So you can kind of see that. 50% of the data falls between 33.5 and 79 on this one. So a lot of the data happens just right here. We're going to end up doing this with calculators and with Desmos, but we did need to know how to do it by hand. And the smallest, the largest, quartile 1, median, quartile 3. Oh, I know a couple things I want to talk about before I move on and close this video. We also want to get what's known as the interquartile range. The interquartile range is the difference between quartile 1 and quartile 3. So if I subtract 33.5 from 79, I'm going to get an interquartile range of 45.5. That means that, and I think I can get rid of data B now because data B isn't real. Well, I guess it's all made up, but anyway. So if I look here, the interquartile range, what I'm saying is there's a spread of 45.5 between quartile 1 and quartile 3. So 50% of the data happens in these 45.5 numbers. And then we also have a range from the smallest to the biggest. So the range itself is 269 minus 2 is 267. So the range goes from the smallest to the biggest. We have a range of 267. So that's a little bit about those two. And also, I would draw your attention to the math notes, an explanation of interquartile range and Bach plots, the 5-number summary, which is the minimum, first quartile, median, third quartile, maximum that we just talked about. The idea that half the data is here, half the data is here, half the data is here, that interquartile range, etc., etc. We ignored outliers. There is a couple of ways to do it, which will probably come up later in class, that you can come up with outliers in this data. But we're going to ignore outliers from now and save that. Really not even in integrated 2. You'll probably get a formal definition in integrated 3, or maybe if you ever take stats. Anyways, that is 2 days of lessons. So if the video is long, just remember it counts for 2. Have a good day.